In this section, you will learn how at the beginning of AI research an attempt was made to develop an algorithm which, with the help of problem reduction, should be able to imitate the problem-solving strategies of humans. You will also learn why the attempt failed in the end. From the mid-1950s to the mid-1960s, AI research was still dominated by euphoric expectations. It was the claim of the researchers to formulate general problem-solving procedures for computers that should be able to solve people's everyday problems on the basis of logic. Newell, Shor, and Simon first invented the logical theorist in 1957. It was a proof program for the first 38 propositions from Russell's and Whitehead's logic book Principia Mathematica. After these successes, the 1962 General Problem Solver program was to establish the heuristic basis for human problem solving. Instead of writing a program that solved exactly one problem, the General Problem Solver was supposed to solve arbitrary problems by means of an algorithm. Aristotle's means-end analysis seemed to be a suitable tool for this purpose, since it is based on the assumption that every goal can be achieved. For this purpose, the goal to be achieved is divided into smaller sub-goals, which, if they are all worked through, will necessarily lead to the desired final goal. Here we see an example from Simon's human problem solving, which illustrates the principles of the method well. The primary goal in this example is to get my son to kindergarten. If my son is not yet in kindergarten, I ask myself what the difference between my current condition and what I want is. In this case, the difference is the distance. So the next question I ask myself is, what changes the distance? My car. My car changes the distance. But my car does not work. What would it take to fix it? A new battery. But who has new batteries? A car repair shop, of course. I want the garage to put in a new battery, but the garage doesn't know I need one. How can I fix this problem, and what is the problem? In the communication. What does communication allow? A telephone. The example can be continued at will. However, the structure of a problem can be described. First, we ask ourselves what the objectives are. Then we look at the conditions that must be met in order to achieve the goals. And are there operators or even means available to transform our state from sub-goal to sub-goal? You now see a possibility to break down a problem, as it is also usual for the programming language Lisp. In the list finish, you will find our target state. The start list contains all states that are initially available. Our operators are defined as follows. We have an action, a condition for the action, a function that adds the state to the currently valid states, and a function that deletes the state from the currently valid states. Below you can see several operators defined here. In order to better understand the example, we would choose a different type of presentation. At the top of the list is the goal to be achieved. The son should be in kindergarten. If my son is not yet in kindergarten, I go to the first operator, drive son to kindergarten. In order for the operator drive son to kindergarten to be fulfilled, two conditions must be met. Firstly, the son must be at home, and secondly, the car must be functioning. We look up in the list when both conditions are fulfilled. The son at home state is present in the start states, but not the car working state. To find out which operator adds the state car works to the current set of states, we go through all operators and see that the state car works is added to the state workshop mounted battery. But the operator workshop mounted battery is again bound to preconditions. On the one hand, there must be the condition that the car needs a new battery. The garage must know about it, and the garage must have the money. In the initial state table, we see that the state car needs a new battery is given. But the states workshop knows and workshop has the money are not. To add the state workshop knows to the current valid state set, we look again which operator adds the state. In this case, it is the operator reports of the workshop about the problem, which again depends on the conditions communications with workshop possible. This state is not present in the initial state set, so we look again which operator adds this state. It is the operator call workshop. This operator in turn is bound to a precondition, namely that the telephone number must be known. We continue analogously by finding the operator that adds the phone number to the current state set. It is the operator find phone number, which is bound to the precondition that a phone book must be available. If we look at the initial state set, we see that a phone book is actually available. The fact that a phone book is available allows the find phone number operator to add the phone number known state to the currently valid state set. This results in a kind of domino effect. Because the telephone number is now known, the operator call workshop can add the state communication with workshop possible to the currently valid state set. The same applies to the operator reports from workshop about the problem. Since the state communication with workshop is now possible, the state workshop knows about the problem can be added to the state set. Now the operator workshop mounted battery has to fulfill the condition workshop knows about the problem. Unfortunately, this does not yet apply to the condition workshop has the money. To add this condition to the condition set, we are looking for the operator who adds this condition. This operator is linked to a precondition, which is money is available. In our initial state set, we see that the state money available is present. So the state workshop has the money can be added to the state set by the operator pay workshop, and at the same time, since the money now has the workshop, it can be subtracted from the current state set. The operator workshop mounted battery has now fulfilled all preconditions and can add the state car works to the condition set. Now that the car is working, I can drive my son to kindergarten. The state that my son is at home is deleted. We were thus able to break our problem down into many smaller sub-problems and consider them as self-contained. This process is called problem reduction, and the general problem solver can be divided into the group of condition-based problem solvers. As we have seen, a problem is formalized by a space of possible states between which transitions are made by means of operations. Even with our small problem that the son had to be driven to kindergarten, numerous constraints have arisen. In the problems of the real world, therefore, state explosions quickly arise which can no longer be controlled. In addition, the assumption that the machine could solve general problems with a general problem solver is not correct, because the human being has to enter states manually. In fact, for the reasons the general problem solver could only be applied to well-defined problems, such as proving simple theorems from logic and geometry, word puzzles, or chess.